Hi everyone, welcome back to Chem Story. Today we're diving into boiling point, melting point, and solubility. These are really fundamental concepts in chemistry because they help us understand how substances behave depending on their phase and the conditions they're in. Whether you're in the lab, developing new materials, or exploring biological systems, it's super important to know how intermolecular forces affect these properties. Alright, let's kick things off with the boiling point. Boiling happens when molecules in a liquid gain enough energy to break free from the intermolecular forces holding them together and escape into the gas phase. In other words, they need just enough energy to overcome those attractions and become vapor. The stronger the intermolecular force is, the more energy it takes to break them, which means a higher boiling point. So in general, when you're comparing compounds with similar molecular weights, the ones with stronger intermolecular forces will boil at higher temperatures. For non-polar molecules, which only have dispersion forces, also called London forces, there are two main things that affect their boiling point. First, as molecular weight goes up, dispersion forces get stronger, so the boiling point increases. Second, the larger the surface area of the molecule, the more contact it can make with neighboring molecules, and that means stronger interactions and a higher boiling point. Let's start by looking at how different types of intermolecular forces affect boiling points. Take a look at these three molecules, N-butanol, 1-chloropropane, and N-pentane. N-butanol boils at 117.7 degrees Celsius. Why so high? Because it can form hydrogen bonds, and those are the strongest type of intermolecular force. That's why it has the highest boiling point among the three. Now, 1-chloropropane has a boiling point of 46.7 degrees. It has dipole-dipole interactions, which are weaker than hydrogen bonds, but stronger than dispersion forces, so its boiling point lands in the middle. And finally, N-pentane only has dispersion forces, the weakest type. That's why it boils at just 36 degrees Celsius, the lowest among the three. So this trend really shows us that the stronger the intermolecular forces, the higher the boiling point. Now let's see how molecular weight affects boiling points when the main intermolecular force stays the same. A good example is the halogen molecules, I2, Br2, Cl2, and F2. They're all nonpolar, so they rely only on dispersion forces. Here's the trend in boiling points. I2 boils at 184.4 degrees Celsius, Br2 at 58.8, Cl2 at -34.1, and F2 way down at -188. So what does that tell us? As molecular weight increases, boiling point goes up. That's because bigger molecules have stronger dispersion forces, which makes it harder for them to escape into the gas phase. Alright, now let's take a look at how molecular shape affects boiling points. Even if molecules have the same molecular weight, their shape can still make a big difference. Let's compare three molecules, N-pentane, isopentane, and neopentane. All three have the same molecular weight, but very different shapes. N-pentane has a linear structure, so the molecules can stack closely together. That leads to stronger intermolecular interactions and gives it a boiling point of 36 degrees Celsius. Isopentane has a branched shape, which reduces how tightly the molecules can pack. That means weaker interactions and a lower boiling point of 27.7 degrees. And then we have neopentane, which is super compact and almost spherical. Because of that shape, it can't stack well at all, so dispersion forces are really weak. That's why it has the lowest boiling point, just 9.5 degrees Celsius. So what does this tell us? More compact or spherical molecules have weaker dispersion forces and lower boiling points. Now, to sum it all up, there are three major factors that affect boiling points. First, the type of intermolecular force. Hydrogen bonding is the strongest, followed by dipole-dipole, and then dispersion forces. Second, molecular weight. Heavier molecules generally have higher boiling points. And third, molecular shape. Linear molecules usually stack better and have stronger interactions, so they boil at higher temperatures compared to branched or compact ones. Now let's move on to melting point, or MP, and how it's affected by intermolecular forces and molecular structure. Just like with boiling point, the stronger the intermolecular forces, the higher the melting point, That's because it takes more energy to break apart the forces holding the solid together. But there's another big factor when it comes to melting point, and that's how well the molecules pack in the solid state. And that packing depends a lot on the shape of the molecules. More symmetrical and spherical molecules can pack more efficiently in the solid state. That tight packing lets them form a well-organized lattice structure, where the molecules are held closely together. And when they're packed like that, the intermolecular forces get stronger, which means a higher melting point. A stable, tightly packed crystal lattice is harder to break apart, so it takes more energy to melt, again leading to a higher melting point. Now here's something really important to remember. While stronger intermolecular forces increase both boiling and melting points, molecular shape affects them in opposite ways. In the liquid phase, a more compact structure means less surface area for interactions, so the boiling point goes down. But in the solid phase, that same compact shape allows for better packing, so the melting point goes up. That's why you might see two substances with similar molecular weights, but very different melting points. It often comes down to symmetry and how well they can form a crystal lattice. Let's go through a quick example to see how molecular shape affects melting point. Take neopentane and N-pentane. They have the same molecular weight, but their melting points are very different. Neopentane has a highly symmetrical, almost spherical shape, and it melts at -71 degrees Celsius. N-pentane, on the other hand, has a linear structure and melts at -130. So what's causing that big difference? It's all about packing. Neopentane's symmetrical shape lets the molecules stack more neatly in the solid state, forming a stronger, more stable crystal lattice. That's what gives it the higher melting point compared to N-pentane. We can see an even more dramatic example when we compare cubane and N-octane. Cubane is a rigid, cube-shaped molecule. It melts at a surprisingly high 131 degrees Celsius. N-octane is a flexible, linear molecule, and it melts way down at -57. And here's the twist. Cubane actually has a lower molecular weight than N-octane, but because of its highly symmetrical and compact structure, cubane can pack super efficiently in the solid state. That leads to a very stable crystal lattice, and that's why its melting point is so much higher. So these examples really drive the point home. Molecular shape matters a lot when it comes to melting point. The more symmetrical the molecule, the better it packs, the stronger the lattice, and the higher the melting point. Now let's talk about solubility and what determines how well a molecule dissolves in a given solvent. Solubility is basically the ability of a solute to dissolve in a solvent, and how well that happens depends on two main things: the nature of the solvent and the types of intermolecular forces involved. Different solvents interact with solutes in different ways. So depending on those interactions, solubility can vary a lot from one system to another. In polar solvents, one of the biggest factors that affects solubility is hydrogen bonding. If a molecule can form hydrogen bonds with the solvent, it's usually highly soluble, because those strong interactions make it easier for the solute to mix in. For example, alcohols and carboxylic acids dissolve really well in water thanks to their ability to hydrogen bond with water molecules. Now, even if a polar molecule can't form hydrogen bonds, it might still dissolve, just not as well. That's because dipole-dipole interactions can still occur between the solute and the polar solvent. They're weaker than hydrogen bonds, but they still allow for some favorable interaction, so the molecule can still be at least moderately soluble. On the flip side, nonpolar molecules don't dissolve well in polar solvents because they just don't have the right kind of interactions. Without hydrogen bonding or dipole-dipole forces, nonpolar molecules can't mix with polar solvents, so instead of dissolving, they separate into different layers. A classic example? Oil and water. Oil is nonpolar, water is polar, and since there are no meaningful interactions between them, the oil just floats. But in nonpolar solvents, it's a different story. Nonpolar molecules experience favorable dispersion forces with other nonpolar substances, and that leads to good solubility. Because both the solute and solvent are interacting through the same type of force, they mix easily. That's why hydrocarbons dissolve well in solvents like hexane or benzene, but not in water. Now, to wrap it all up, boiling point, melting point, and solubility are all influenced by three key things: intermolecular forces, molecular weight, and molecular shape. Stronger intermolecular forces raise both the boiling and melting points, Molecular shape affects how molecules pack in the solid state and how they interact in the liquid. And when it comes to solubility, the classic rule holds true: like dissolves like. Polar molecules dissolve in polar solvents, and nonpolar molecules dissolve in nonpolar solvents. Understanding these trends gives us powerful insight into how substances behave across different environments. That's all for today's lesson. Great work, and I'll see you next time.